Alright, now it's time to get some serious fun. Alright, so we're going to do some more problems. I'm going to give you 4 more examples on how to use substitution in indefinite integrals, and we'll see how this works. Alright, so I'm going to evaluate the antiderivative of cotangent 7x dx. And now if I go back to the beginning of my notes, it's up there trying to find the integral of cotangent. I don't have the integral of cotangent. But what if I were to change this up? What if I were to come here and say, well, this is going to be the integral of, well, that's the same thing as saying cosine of 7x over sine of 7x dx. And again, with practice, you're trying to think, well, what should u be? Well, what if I choose u to be sine of 7x? And du dx is equal to, well, sine of 7x. Oh, this looks like a chain rule problem. So it's going to be cosine of 7x times derivative of my chocolate, 7. All right, now I'm going to solve for du. So when I do that, du is equal to 7 cosine of 7x dx. Well, look, I'm getting close again. That whole cosine of 7x dx. So again, I divide both sides by 7 is equal to 7 cosine, oops, not 7 cosine, of just cosine of 7x dx. Again, I take a look and I say, oh, hey, look, cosine of 7x times dx, cosine of 7x times dx. I'm going to do all my substituting in at once. So now I have the integral. Okay, I have let's see here, the sine of 7x is just going to be, let's see here, u. The cosine 7x dx is 1/7 du, so the du goes here. The 1/7 part I can automatically bring out over here, but what's left on top? Just a 1. Okay. Well, alright, well what function gives me the derivative of 1 over u? Oh, well, that's just natural log. So that's the integral, not the integral, but this is equal to 1/7, okay, natural log of u plus c. But I don't want u, again, I want x. So I replace it, and this becomes equal to 1/7 natural log of sine of 7x plus a c. Multiply everything by 1/7, and is equal to 1/7 natural log sine 7x. Again, still a plus c, because remember, it doesn't matter. It will always be a plus c. It doesn't matter if I multiply by 1/7. It's still a number, and when I take the derivative of that number, it goes away to be 0. Okay. Now, as a refresher for your natural log powers, that's not the answer. You gotta remember that 1/7 times the natural log of something is, whenever it's a number times the natural log, it's really like saying the natural log of sine of 7x raised to the 1/7 power. Okay, so that could also be, an answer. They're both the same. All right. So let's go ahead and let's take a look. We got 2 examples on the next one. I'll take a look at these next 2. Okay. This first one doesn't seem so bad. Why? Because again, when I take a look at my integrals, my table of integrals, what I'm supposed to be doing is I have to think, what function, when I take the derivative, do I get secant 2x, tangent 2x? And you'd be thinking, well, I get something close. I know that when I take the derivative of tangent, when I take the derivative of secant, I get secant tangent. But I don't know about this 2x business. So again, that's where I got to set up my u. Okay. U needs to be 2x. du dx is going to be equal to 2, and I find that du is equal to 2 dx, and that 1/2 du is equal to dx. So now when I do my replacements, I now have the integral of secant u, tangent u, dx. Well, what's dx? Dx is 1/2 of du. So I'm going to put du here. My 1/2 goes all the way out here. And again, this is where I say, oh, now I know that secant is going to be secant tangent. So when I take the integral, it's going to be secant 1/2 secant u du plus a c. Oops. Didn't put my parentheses in the right spot. Plus a c. I go ahead and multiply the 1/2 through, and I go ahead and put in 2x for u. I get 1/2 secant of 2x plus a c. Again, there's my answer. Switch over here. I have actually an issue on this one. Again, on your notes, this should be a 3x on the inside. That's a mistake on my part. Okay. Well, now I go and I take a look. Well, the square root of tangent 3x secant squared 3x. This is getting annoying. I have no idea. So we need to start trying to figure out what's the process that GL uses here, and I gotta be going to choose a u. So we've done enough of these now to where you should see the process. My process is when I choose a u, I know that I'm going to have to take the derivative. And when I take the derivative, it probably is going to cancel out what's already there. So what I want to do is I want to pick a u that when I take the derivative, is going to equal another piece of what's already there. So if I were to choose, and I go around through and I say, well, what if I choose u to be secant squared 3x? Well, do I know the derivative of secant squared? Yeah, but it's kind of messy, because it's secant times secant. I'd have to use a product rule. It's going to be messy, and I'm not going to end up with the, square root of tangent 3x. Well, if I just choose 3x, well, then I take the derivative of 3x, and it's just 3, and nothing really cancels out. That's not going to help me much. Well, what if I take this whole square root of tangent 3x and use that as my u? Well, again, I can do it, but it's a chain rule, and it's very messy, and I end up with lots of other things. But then it kind of dawns on me, well, what happens if I use u to be tangent of 3x? And it's just that. It's a process of elimination. It's a process of going through. It's a process of knowing these and doing just lots of problems with it, which is why I'm giving you lots of problems, so that you can go and see and start recognizing where these u's come from. If I choose u, then all of a sudden when I take the derivative du dx, okay, that's going to again be secant squared of 3x, okay, times derivative of 3x, which is 3. Solve for du, and I find out that du is equal to 3 secant squared of 3x dx. Divide both sides by 3, I get 1/3 du is equal to secant squared 3x dx. Alright, so then I go and I start plugging things in, and I see that my integral, now it's the square root of u. Okay, well, again, look right here. Here's secant squared 3x dx, secant squared 3x dx. Oh, so all of that is equal to this 1/3 du. So again, I'm going to take the 1/3, put it out here, take the du, put it right here. I want to rewrite this, so now I have 1/3 the integral of u to the 1/2 power du. And now I use that whole power rule that's up there, okay? And I have 1/3 times. All right, so add 1 to the power. 1/2 plus 1 is 3/2. Divide by 3/2. Well, that's the same thing as multiplying by a 2/3. And don't forget the plus c. And I find out that 1/3 times 2/3, okay, is 2/9. U is really tangent 3x, tangent of 3x, all raised to the 3/2 power, plus a c. And there's my integral. And you gotta be going, oh, how crazy cool is this, right? Look how powerful this is. You're giving this as an answer, you're undoing it and getting that. That's amazingly cool. You have to be in awe of that. How cool is that? I'm getting goosebumps right now. All right? One more and we're done. Get to this one. There's actually 2 ways to solve this one. And I want to show you that both ways work. All right? So again, the first one is go about our normal business. I want to try and find something that I can substitute in for. Well, what can I substitute in for? Oh, I can see that, well, if I take the derivative of sine, it gets me negative cosine, but then it doesn't get rid of both cosines because there's cosine squared. But if I choose cosine squared, that's not going to work either because it's going to get messy. But what happens if I just choose cosine? If I just choose cosine to equal, my u, and then when I take my derivative, again, dt, okay, du dt is going to equal negative sine of 2t plus 1 times the derivative of my chocolate, which will be 2. Solve for du, okay, divide both sides by negative 2, so I get negative 1/2 du is equal to a sine 2t plus 1 dt. Again, now when I plug in, what I need to be seeing here is that I have the integral of, well, cosine squared, well, that's going to be u squared, sine 2t plus 1 times dt. Here it is, sine 2t plus 1 is going to be negative 1/2 du. The negative 1/2 can come out here. Du goes here. Oh, that means it's 1 here. And I'm going to rewrite this as just the integral, the negative 1/2 times the integral from u to the negative 2, du. So again, I use my power rule and to find the antiderivative. And so it's going to be negative 1/2. The power rule says add 1. Negative 2 plus 1 is a negative 1. Negative 1 divide by a negative 1, which means negative. Oops. Don't forget the plus c. I go ahead and substitute in there. I get a negative 1/2. Or now becomes a positive 1/2. U to the negative 1 is the same thing as sine 1 over cosine of 2t plus a 1 plus a c. And this is where you have to see, well, it's 1 over 2 cosine, 1/2 times, well, 1 over cosine is the same thing as saying secant. So this is 1/2 of secant 2t plus 1 plus a c. So how does that happen to get it here to be at a second way? Well, I can recombine this. I can say my integral is sine over cosine. Sine over cosine, that's tangent. So I can rewrite this as tangent of 2t plus 1 times, well, 1 over cosine is what's left over. Well, 1 over cosine is times secant of 2t plus 1. And this turns into a big problem just like the one back over here. Very similar to it. In fact, if I make 2x plus 1, when I take the derivative, I still get the same derivative. So my answer is going to be the exact same thing. I'm not going to rehash it, re-go through it. You already see it over there. So it ends up being the exact same thing of just doing it of 1/2 of secant 2t plus 1. Now if you want, for your own, plus a c, for your own work, you may want to, down in here in this space here, work it out. Choose your du and work it out using the previous example as a workout problem. Okay? So there are multiple ways to solve this. You still get the same answer. Still mind-blowing that math works in that way, right? All right, so here's your assignment. There it is. Okay, remember Demana, that's your book. So if you can't read the problems in there, good news, you can go to your book. And then here's Canon, 2 sections from Canon. All right. It may seem like a lot. It's, it's a little bit. You need to come with questions. All right. You need to watch these videos. Talk to you guys later. Bye.